Good day. Today we'll be looking at other forms of limit of functions, which is known as indeterminacy forms. There are many functions whose, when finding the limit of those functions, their limits give the form 0/0 or 0 raised to the power of 0 or infinity raised to the power of 0, infinity minus infinity. We also have other forms such as infinity divided by infinity. We also have 0 multiplied by infinity, etc., etc. So we want to look at some functions whose limit give us this form. Though these forms look like numbers, they are not. They are called indeterminacy forms. This is because these terms do not have any value. We can't call them a number. They do not exist on the real line. Hence, they are indeterminate. So here we'll consider a few examples of functions that give us any of these forms. So for example, we'll be looking at these three examples. The first one will be what we have there as the limit of x squared minus 5x plus 4 divided by x minus 1 when the limit of x tends to 1, and also 2, the limit of x ln x as x tends to 0, and the limit of 1 over x minus 1 over absolute value of x as x tends to 0. We'll be looking at this one after the other. So here, when we substitute for x, we have 1 squared minus 5 into 1 plus 4 divided by x minus divided by 1 minus 1. So when we compute this, you see that 1 squared is 1 minus 5 plus 4. That will give us 0. And also the denominator also give us 0. So this is what we refer to as a indeterminate. Okay, we call it indeterminate because this does not have value, either finite or infinite value. It does not. So, and it is not a number. So how do we do this? We can rectify this function. The reason why we are getting the result is that this function is not well put. So in order to write it in a way that it can be, that we can find the limit. So what we do is we simplify. And how do we simplify? Okay, so we'll write this numerator in the form, let's say, by simplifying so the limit gives the limit of x squared minus 5x plus 4 divided by x minus 1 as x tends to 1. So this is equivalent to this. Okay, so by expanding this, we get this numerator. Okay, so here x minus 1 is common, so this can cancel out. So at the end, we have the limit as x tends to 1, x minus 4. So here, when we substitute 1, here, what we have will be 1 minus 3, and this gives negative. So, sorry, this is a 1 minus 4, and this gives negative 3. So the limit of this function is not 0 over 0, it is negative 3, as seen here. So the limit of this function is negative 3. Also, for example 2, if we substitute for x, here this will be 0 multiplied by length 0, and this is equal to 0. When we press the calculator to evaluate length 0, we get negative infinity. So this becomes negative 0 multiplied by infinity. So if you recall, 0 multiplied by infinity is under indeterminacy form, as given at the beginning of this class. Okay, so this also means indeterminate. So what we need to do is to simplify this also. But in order to simplify this form, due to the one of the function being transcendental, we apply what we call L'Hopital's rule. How do we do this? So to simplify this, we apply L'Hopital's rule, which says if you have a limit of a rational function equal to 0 over 0, or any of the indeterminacies, okay, so what we do is that we say that the limit of that rational function is the same thing as the limit of the slope of the numerator here over the slope of the denominator here. This will be the same if the limit of this is 0 over 0 or any of the indeterminacy form. So we are going to apply this to this limit, because this gives us one of the indeterminacy form. So now, using the L'Hopital's rule, we have that the limit of x, which is this, will be equal to the limit of linearness all over 1 over x. Okay, so you see that when we take the reciprocal of this x, okay, this is similar to this. Okay, so this line looks like the form of a rational function. So applying the L'Hopital's rule, we differentiate the numerator here. So by differentiating the numerator is differentiating it is 1 over x. Okay, and differentiating the denominator, we have negative 1 over x squared. So we can get this form in any of the standard textbook of calculus. So the derivative of linearness, which is 1 over x, and the derivative of 1 over x, which is negative 1 over x squared. So when we evaluate this, this becomes, okay, when you divide what we have here, this, we haven't applied the limit yet. Okay, we haven't applied, so until we finish the simplification. So when we divide this, what we have here is negative x. So if we substitute for for x, okay, so here we have negative 0, which is what? 0. Okay, so the limit of this function x ln x when x tends to 0 is actually 0, as we have seen here. Okay, and let us come again to clarify some of the things we do here. So because we have indeterminacy form for the function, we have indeterminacy form, which is this. So we have said this is not a number. Okay, so now to check whether the limit of this function exists or not, we need to redefine this function, And how do we redefine? We redefine using the method of L'Hopital's rule. So, and that's what we have said earlier, how we apply the L'Hopital's rule. So before we can apply L'Hopital's rule to this, we need to change this to a rational form of functions, which we have done here. Okay, so reciprocating this x, okay, it comes to the denominator this way. So when we apply the L'Hopital's rule here, we say we should differentiate the numerator and differentiate the denominator. So we have what is here. So when we simplify this by removing some terms, this reduces to the limit of negative x as s tends to 0. So when we apply the limit, so we get negative 0, which is 0. So for the third example, which is the limit as s tends to 0, 1 over x minus 1 over absolute value of x. Okay, so again, when we apply the limit, this will be 1 over 0. Okay, and this will be minus 1 over absolute value of 0. Okay, this is 1 over 0 is infinity. Okay, so absolute value of 0 is 0. Okay, so 1 over 0 is also infinity. Okay, so this is under indeterminacy form. Okay, so which means we need to redefine this function in order to, before we can evaluate. So by simplifying this function, so due to the absolute values here, okay, so this value of this function means two things. Okay, due to the absolute value there, it means we can write this function as the limit as s tends to 0, 1 over x divided by x, where this is when this x, when the absolute value here is positive, so we can write it as this. So meaning it is positive here. Okay, and similarly we can write this as this. So when the absolute value is negative, okay, so this is supposed to be minus x. So due to this negative here, so negative here will affect the negative here, so this will become positive 1 over x. Okay, so here when we evaluate this further, okay, when we simplify this further, 1 over x minus 1 over x is 0. Okay, so we haven't applied the limit yet, so this is 0. That is 1 divided by x minus 1 divided by x. Okay, that is 0. So, and then the limit of this 0 is a constant. So the limit of a constant is 0. Is that constant? So the limit of 0 is 0, irrespective of what is there. So since this is a constant, so the limit of this will be 0. Okay, so that's 0. So also for the second one, here we have the limit 1 over x plus 1 over 2x. Again,